Hello friend, welcome to new video of a unit 5. In a unit 5 we need to do the study of the steady state heat transfer problems. In this slide we need to do the study of the governing differential equation for 1D steady state heat transfer. But in this chapter we need to do the study of a lot of things. This is the very important chapter for the final examination. In this one we do the study of a one-dimensional steady-state heat transfer problems, as well as we need to define or the formulate the governing differential equation, then the finite element formulation using the Galerkin approach for the composite war and the thin film. Similarly, we need to understand what is meant by the essential and the natural boundary conditions and solving for the temperature distribution. It looks a very small unit, but it has a lot difficulties, because in this chapter you need to have a knowledge of a heat transfer in a right way, then the finite element analysis, then the formulation of a strong form to weak form by using a Galerkin method, and then formulating the element stiffness matrices, and then manipulation of this finite element stiffness matrices in a right way. So let us move first of all, that is defining the different types of the differential equations. So now first of all, the governing equation, you knows very well, in a heat transfer process there is a three important topics, that is the conduction, convection and the radiation. So first of all we are going to know what are the different types of the governing equations for the conduction. You knows very well, in a governing equation for the conduction, that is the heat is directly proportionate to the negative temperature gradient. Now heat flux, that is the Qx is equal to minus k dt by dx. Now you knows very well this equation is also called as the Fourier equation, and this one is as per the dimensions. So if this one is the 1D problem, then that is the Qx is equal to minus k dt by dx, dabba t by dabba x. Qy is equal to minus k dabba t by dabba y, and Qz is equal to minus k dabba t by dabba z, where the Qx is the heat flux in x, y and z direction with a unit of the watt per meter square, while dabba t by dabba x, dabba t by dabba y and dabba t by dabba z is the temperature gradients in x, y and z direction with a degree centigrade per meter, and K is the thermal conductivity. The unit is that watt per meter per degree centigrade. Now these one are the governing equations for the conduction. Now find out the governing equations for the convection. So governing equation for the convection is the different than the conduction. So governing equation, that is Qh is equal to H into TL minus T infinity, where the QH is the convective heat flux in watt per meter square. Now let's see here, in a conduction process, that is the Qx, that Qx, this Qx, the unit of a Qx here, that is the W per, that is watt per meter square, watt per meter square, and this temperature difference is the degree centigrade per meter. Here also you see that is the QH, that is the heat flux is watt per meter square, and the H is equal to heat convective heat transfer coefficient, watt meter square per degree centigrade, while this one is the degree centigrade. So convective heat transfer, while here the K also is somewhat, K is equal to thermal conductivity, that is watt per meter degree centigrade, while H is H sorry H is equal to watt per meter square degree centigrade. Why this is the meter square degree centigrade? Because here we are considering the surfaces. Convection is taken place through the surfaces, that's why surface area we have considered, and that surface area is in terms of the meter squares. That's hence we are considering this one is the meter square degree centigrade. Now the third governing equation for the radiation is, that is the heat flux watt per meter square is equal to QR, radiation is equal to, that is sigma T to the power 4, where the sigma is the Stephen Boltzmann constant, and with a unit of W, that is the watt per meter square degree Kelvin. while the other units are the degree centigrade. Okay, so here Kelvin to the power 4, and this one is the T is the absolute temperature of a surface, that is the degree Kelvin. So these are the three different governing equation for the conduction, convection and the radiation. Let us move on finding the governing differential equation for 1D steady state heat transfer problem. Now what is mean by the steady state? What is mean by the steady state? So the steady state means what? That just whenever your heat transfer is not related with the time, then that is called as the steady state problem. And dynamic problem, when your heat transfer is taken place with respect to time, then that is called as the your dynamic heat transfer problem. So here we are not focusing on a dynamic, but instead of that we are focusing on the steady state heat transfer problem. So by using this one, we are finding the differential equation for the 1D steady state heat transfer problem. So let us take the cube. Now this cube is insulated with certain surfaces. So this surface is insulated, this surface is insulated. So top and down surfaces are insulated. So the two sides are insulated very right way. Then these surfaces, that is the A, B, C and D, this surface also insulated, this surface also insulated. And opposite to that, that is the E, F, G, H side also insulated. So that all the side 1, side 2, then opposite to that 3, and this one is the 4. Four sides are insulated. Hence there is a heat transfer taken place only through this way. So along x-axis only. So this is the qx, that is the heat flux is moving from this one to this one. So that is equal to qx plus dx, qx plus dx. So this is the heat flux is traveled or the transfer from this position along the your x-axis, while the other surfaces are insulated. Hence there is no flow towards this direction, no flow towards this direction, as well as there is no flow towards this direction or the vice versa. Only the movement, the flow is occurs into this direction and into this direction only. So this is the 1D problem. That's why this is the 1D. So in a 1D problem, what is the energy balance? You know that there are the more importance in a heat transfer problem, that is the mass balance, momentum balance or the energy balance. So in a energy balance, the elements during the time dt, that is equal to heat flow, heat inflow plus heat generated is equal to heat outflow plus change in internal energy plus change in internal energy. This is the energy balance equation for the elements. Heat flow plus heat generated is equal to heat outflow plus change in internal energy. Now now that is the heat flow, that is heat inflow. So heat inflow is the qx. So qx multiplied by, now there is a towards the dx direction there is a flow is taken place, that's why this dx is not considered here, but dy dz along the time t. So this is the dt also available here, plus q dx dy. Again the q is moving towards the dx dy dz, where the q is the rate of the heat generation. So heat generated along all these three parameters, because the heat is generated in a volume, that's why we have considered all the three values, that is the dx, dy and dz. While here we have considered only dy and dz because the heat transfer taken place along the x-axis, hence dx is not included here, but q, that is the heat generated, is into the volume. That's why this is the dx by dy plus dz into dt, that is equal to heat outflow. So heat outflow is equal to, that is qx plus dx, into dy dz into dt, into dt. Again here there is no dx, hence plus that is the change in internal energy, that is equal to rho multiplied by, that is the density into the volume, that is dx dy dz into cp into dt. That is the q is equal to rate of the heat generation per unit volume within the element, that is W per meter cube. dt is the rise in temperature, and Cp is the specific heat of element, that is joule per kg degree Kelvin, and density, that is the rho, is equal to density, that is the kg per meter cube. So these values are here for this one. Hence what we are getting, when that is the qx dy dz dt, q multiplied by ds dy dz into dt, that is equal to qx outflow, that is qx plus dx dy dz dt plus internal energy, that is this is the internal energy. So that this is my inflow, this is heat generated, this is outflow, and this one is my change in internal energy. Now by manipulation, what we get, this qx and these terms, these two terms are looks constant same one, so this one is minus this one, so qx minus qx plus dx dy dz dt plus q into dx dy dz dt is equal to my change in internal energy, internal energy, that is the rho into dx by dz dcp dt. According to the Fourier's law, qx is equal to, that is the heat flux is equal to that minus k into dt by dx, as well as qx plus dx is equal to that qx is equal to qx plus, now for this dx is equal to, that is d by dx into, that is dq by dx into dx, d by dx. Now there is a variable is required, and that variable is dx, so dx by dx, hence, and what we required here, the q dq, because there is a small change, so qx is not there, but the small dq change, dqx is the small change, so this is the dqx is the small change, so dqx is the small change, that's why this is the dqx divided by dx. And just to minimize this one, here also we put the dx, hence that is the qx plus dx is equal to kx plus d by dx dqx upon dx into dx. Hence this is equal to minus k, this qx is equal to this value, put here this value, so minus k dt by dx minus this value d by dx into, that is dq by dx is this one, that is the k into dt by dx into x into dx. So this is the value for qx plus dx. Now these values are manipulating, so this is the qx minus, this is minus qx, this is the plus qx. So see here, so here what we studied, this one is the minus q dx, so here this one is the minus q dx is putting here. Now this one is the minus minus, this one is the minus plus, so this is the minus, so for this term we are putting this value, so this minus is comes to plus, so here we observe this here, that is minus k dt by dx plus k dt by dx plus, that is d by dx k dt dx into dy dz dt plus your heat generated, that is the q into dx into dy into dz into dt, and change in internal energy, that is the rho into cp into dt into dx dy dz. This rho, that is the density multiplied by volume, so this is the my change in internal energy. So what we get, this is the cancel, this one is cancel, so we get, that is the d by dx k into dt by dx into dx by into this, now this dx is available, so d by dx here, this term, this is the term d by dx, so this is the term is available here, then this is the dx dy dz into dt plus q into dx dy dz dt is equal to rho cp dt dx dy dz. Hence what we get, this dx dy dz is cancelled, this also cancelled, this also cancelled, left hand side is equal to right hand side. Hence what we get, that is the dA by dx k dt by dx into dt, because dt is remain, this dt is remain, this dt is also remain. So q into dt is equal to rho cp dt, rho cp dt. Now here this one are the dt is same one, so this one is terms combined, and this dt if we transfer here, that is here if we put this one, then that is the temperature gradient. So in the next step, what we have given, what we have done, that is d by dx k into dt by dx plus q is equal to rho into cp by dt by dt. Hence for the steady state problem, dt by dt capital T by small dt is equal to 0, is equal to 0. Hence this value is 0. So this term becomes 0, this term becomes 0, this term becomes 0. Hence what we get, that is the d by ds k into dt by d small t dt by dx plus q is equal to 0. Hence by differentiating this term, so this is constant, so constant come out. Now the differentiation of this with respect to x, hence d square t upon dx square plus q is equal to 0, where q is playing the very vital role. So what that q is suggesting, if it is minus, it is minus when the heat is lost, when the heat is lost. What that, it is a plus, q is a plus, it is a plus or minus, but when plus when the heat is generated, means the heat is added, that time plus, or when the heat it is minus, when the heat is lost, or this is the sink, this is work as a sink, okay, sink, and this one is the source, this one is the source. So source is positive, and sink is negative. Hence this is my formula, this is my differential equation, for the steady state heat transfer problem for the 1D. Now if we have taken the 3D problem, then the formula looks like this one: k into dt d square t upon dx square plus k into d square t dy square plus k into d square t dz square plus q is equal to 0. So this is the 3D problem, this is the 3D problem, while this is my 1D problem. So this is my 1D problem. So this is my differential equation for the heat transfer for 1D, unsteady steady state problem, for the steady state problem. So keep in mind, just remember this one, because this formula plays the very important role in the next lecture. Thank you for watching the video.